Yes. Oh, just the title. The main point of this talk, actually of the whole activity here, is that let me begin with for some special hyperbolic nodes, right? Long statements, including celebrated A, well, M, and 42. Right? So before I continue, so what is remarkable of this particular guy? It is really maybe the most famous hyperbolic node, even more famous than figure 8. So we will discuss it. Of course, I will say something about this, but anyway, there's some list of nodes right now, quite special actually, right? But we will see what will happen in the future. Okay, then comma, right? KHR reduced to with conversion reduced, right? Is Motivic. Meaning it is count of point of some stack, Artin stack here, right? FK with some weights, right? So there will be some weights. T will occur and A will occur. They will be forming, right? A will occur. What is about Q? Q will occur just because of this finding. Okay, so this is exactly the fact, right? The main point. So 3 months ago, I called a sort of similar talk, but now I know much more actually. At MIT, I call it surprising development, right? So let me explain quickly what is surprising. So first of all, of course, hyperbolic. Hyperbolic nodes are as non-algebraic as possible, right? There's a little something about, I'm supposed to say something about a polynomials, maybe about something else. But if you look at this particular guy, or classically, we're supposed to do the following, right? And then take a universal cover, which is H3, and so on and so forth. Anyway, there are a lot of stuff, mostly due to Thurston, a lot, right? This is hyperbolic, there's canonical hyperbolic structure, your universal cover here, discrete groups and stuff like this here, right? Whatever you are doing, still it is non-algebraic from any perspective. And it is just impossible that it can be just so simple, you know, right? So this thing not just associated naturally, but it captured Havana-Frazansky, literally, right? So this is, of course, surprise, surprise, surprise. Second surprise, there will be 3. Whatever I'm doing, I have 3 months for experiments here, whatever, this level or some other level still. Technically, you can say that it is a manifold, right? Look at the open manifold, etc., etc. Look at this particular guy. Can we say something reasonable using all techniques you wish? So I tried, so far no progress. There is no immediate geometric explanation. What is special, including this very well-known guy here, which is really the most famous hyperbolic nodes. Actually, figure 8 is most known, but this is the most famous. There are papers about this particular one. Just. Famous because there are some papers when people use it to construct some exotic differential structures a lot, right? And then interesting story. What is gamma? What is representation of this gamma? What is uniformization? A lot. Many questions here. But anyway, this business called hyperbolic complex geometry for specialists in complex analysis, real complex analysis about this particular stuff here, about SU to 1, etc., etc. So there is a lot of interesting information here. This is different story, you know. We don't with 16 crossings, there are 2.5 million hyperbolic nodes here. It is for us, right? But for specialists, such remark. 12. Sorry, guys. 12 crossings, and this is just a number, right? Yeah, but mentioned to specialists 242. They will know. Figure 8, of course, everyone knows figure 8 here. But anyway, the first point is that from any perspective, right, presumably including physics, but I need to talk seriously with physicists. From any perspective, there is nothing algebraic of this particular nature here. This is stack and a very nice, very simple guy here. Of course, I will define it. This is exactly his instanton slice. Okay. First, second, this is literally double arithmetic, literally, right? And it is not what we expected. We means many people, including Banishev, including many people, including Braverman, Kazdan, myself, of course, right? Not what we expected. Kapranov, let me mention Kapranov. Double arithmetic means that you have two parameters. You have, for instance, Kac-Moody with two parameters. This is one possibility. But mostly we are discussing p-adic, some kind of combination. P-adic with one parameter, something like this, right? Not what we expected, right? And the third, and maybe the most important, that I replaced compactified Jacobians I will define them. Jacobians exactly by these slices. IS instanton slices here. But what is this particular guy here? It is ASF, affine Springer fiber of type AN. Exactly, right? So affine Springer fibers play a very interesting, actually, core role in modern geometric representation theory, connected with Hitchens system pretty much with everything, you know, right? If something happens at this particular level, if there is some bigger, much bigger, you will see, theory of ASF here, which produces such nice stuff here, then definitely you can expect changes where, including definition of Kac-Moody. Kac-Moody, pretty much everything we do with the reservation about maybe W algebras and Dachais is somehow associated with curves, you know, right? Kac-Moody, parameter, one parameter, y1 parameter here. So here we have definitely some stuff about instantons, almost by definition, instantons means something like C2, right? And this is uniform definition, no X and then Y by induction, no nothing, literally. Who knows, maybe it can be connected with surface. Anyway, I need to talk to physicists seriously. Okay, again, if something happens at this particular level, expect changes, including fundamental lemma, including Hitchens system. It is directly connected with Hitchens system here. What will happen, I don't know. I had only 3 months for this, and I'm doing something else. I'm doing algebraic, combinatorial, etc., stuff. Okay, so here we are, 1, 2, 3. 1, 2, 3, surprise, 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 right? And then this is not even not an introduction, just to say what I'm going to do. Just theorem 1, 2, 3, 4 here, and one conjecture. One conjecture. At MIT, there was theorem 1, 2, 3, and no conjecture. So there is really quite a progress already, you know, right? And this is really very fluid field. Okay, but on the other hand, still, let me do the following. Let me begin with some very fast review of superpolynomials. Otherwise, I just to put the perspective and just to explain what I'm going to do. Polynomials, right? Maybe it will cost me theorem 4. We will see, right? Maybe I will have no time. We will see. Oh no, conjecture will stay. Conjecture will still definitely. Okay, so what we know about superpolynomials quickly. AHR, right? Reduced, as I mentioned. The origin of everything. The next level, H. Daha, UTA, right? Anyway, the 4 theories, right? And 6 theories, 6 connection conjectures. So this is the first connection. Just called connection conjecture. Pretty much all of them are open with a reservation about torus nos. I will say a little something about this. Just connection conjecture, no special knowledge. Next level, Motivic theory, which I'll discuss today. H Motivic. Same, surprise, surprise, but Q will be a cardinality of finite field. Unless I use some kind of special cogomology theories like Borel-Moore or whatever. But anyway, QTA, right? Theory number 3 and L function. And here, surprise, surprise, I need to change the parameters. Change, right? Okay, so Daha is absolute champion with colors and with links, right? The best we have, but only for iterated torus links. Here in this particular theory, still in spite of usage of surrogate modules, still links and colors, especially colors, are difficult, real difficult. Not only technical, even theoretical, because especially because it is reduced story. Okay, Motivic story, right? Again, restriction. Algebraic, which I'll remove during my lecture here. Algebraic links. Colored, but colored only by rows, right? So it will be letter N, right? Colored by rows here. Here arbitrary, absolutely arbitrary, Young diagrams, etc., etc. So this is L function. The origin Galkin. 1973, right? L function of what? And this business of plane curve singularities. This I will explain. Then ORS, then Store wrote a very important. Galkin, what Galkin did? First of all, generality. This is algebra, so Gorenstein, which are more general than plane curve singularities. Gorenstein, rings, generality of this particular business. So then ORS, right? Conjecture. Oblomkov, Rasmussen, Schende here, they pretty much use the same definition of L function, first zeta, then L function, but in some Motivic setting, we're using some kind of, anyway, different Motivic measure. We say technically, we say different Motivic measure. Okay, this is ORS, pretty much the same stuff, but geometrically. This is just basic theory. What Galkin did, he proved functional equation. Functional equation, so I will discuss it in a moment here. Functional equation is exactly the key point here. And of course, it will be the key in my talk. Okay, so. Huh? So here we have Q, now FQ, right? T is technical parameter. T is Q to minus S classically. T is Q to minus S here. A is A, stabilization, right? Not present in Galkin, but now we know very well what I mean. This is just uniformity, right? And of course, colored were not present here, right? This was uncolored. Here you can add colors, but with the same restriction. This is rank. Right. Perfect, right? And look, this conjecture we expected is sort of standard is from algebra to algebra, after all, no topology. It appeared to be reasonable, but appeared to be real difficult because of this particular stage here. Look, here Q is cardinality of fine field. Here Q is cardinality, so you do something absolutely legal. You divide Q, which is a number like 2, 3, 5 here, divide by T, a complex parameter here. So even if you do it for trefoil, I will show it in the beginning will be just the example of torus knots, including trefoil. It will be quite an interesting calculation. This is requires like 2 minutes, I don't know, of calculation. This requires maybe 15 minutes of something, and then at a certain moment you will see that this substitution will appear algebraically because of anyway, no reasons for this, but it will occur, right? Just to say. So just let me put here some names. ORS conjecture is from this guy to this guy, non-reduced KHR here. So here we are, right? Let me put here some names. So this particular stuff is generalized almost certainly, but there must be some several papers about this. Generalized shuffle conjecture. Shuffle conjecture, right? This particular guy, jargon here, field versus Quot. What I call them simply H equals L in my papers, right? The name of this particular guy here. This is just a connection conjecture. That's it. Right? More or less what I want to say. Few questions, maybe late, maybe not today. But you can ask questions anyway, right? So here we are, right? The picture. Again, as I mentioned, pretty much all of them are conjectures, so 6 conjectures. But with torus knots, mostly thanks to Anton Malik here. So for torus, we pretty much know this particular stuff. Again, there must be special to identify H Daha, which is what he is doing. But anyway, here the story is better. And here is some confirmation, but mostly just very, very little confirmations here. Uncolored. For Anton, definitely uncolored. The whole story is uncolored, right? So this is exactly the picture, right? And physics is extremely interesting in this business. With KHR, it is long discussion. Let me at least put here BPS, right? But there are many things. I will skip it completely. So here, definitely this business is super conformal field theory. Daha definitely belongs to this particular direction. By the way, there's Coulomb Daha symplectic dual here coincides with itself here. I will skip it, but anyway, Coulomb and Higgs branches here are nothing else, appear to be nothing else but two definitions of Daha. The first is in terms of fundamental group of elliptic configuration space. The second is K-theoretic, right? So they are literally coincides, Coulomb, and because it is two independent definitions of the same object, it is just self-dual here. It's just special feature about this particular one. So what do we have here? Definitely Landau-Ginzburg sigma model. Landau-Ginzburg sigma model. Let me explain why. So it is about algebraic rings and plane of singularities. So here we are. It's a Waffa-Warren story about local singularities here. So here we are. We have superpotential here. Here we have exactly the guy, which is this particular plane of singularity. So just to connect it. So here we are, right? One of the most fundamental relations is exactly from superconformal field theory to Landau-Ginzburg sigma model. So here we have like affine spaces, like affine Grassmann, case theory, etc., a lot of stuff. Actually, it is Daha is about KZB, about QKZ, and stuff like this. So definitely we know the origin, right? The origin superconformal field theory with some simplifications, of course. And here we have this particular guy. So what happens if you go all the way to the end of this particular mini picture? So it appears that first Z, L is defined as in classical arithmetic. First zeta function, and then L. So this is nothing else but partition function. By the way, here, let me be a little bit more specific, topological, of course. So we ignore modes. Modes are not considered topological. Topological Landau-Ginzburg model. Otherwise, it is just put it here. Okay, so partition function, Z, exactly Z from arithmetic, appear to be nothing else but partition function. So one of applications, there are many applications here. One of application, you consider Witten index, which is nothing else but mu in this business, a Milner number here, and you establish QT split, right? Long ago, Andrew wrote a paper about BPS index with people here, right? So here you do the same for Witten index, and more importantly, for rho invariant of this particular guy. So this is already geometry, spectral geometry. So you consider S3, and for Neumann, rho invariant of this particular guy here. So it appeared to be, there's some paper, but only in the context of algebraic links, actually in the context of this particular picture here. So I found that there are some, if you know superpolynomial, you can capture this particular guy, which is spectral, geometric spectral invariant. Rho means for Neumann invariant connected with Zatia, Pettit, Zinger, etc. here. So connected with superpolynomials. Okay, perfect, right? So this is really impressive application. So there is Milner number here. Here we have Q, we have split, right? Now all the states, all elementary particles will be simple, of course, right? Explicit formulas are extremely nice combinatorial. Okay, this is exactly what I'm going to say. And then now let me go to definitions, and pretty much I populate. So I will discuss only this particular corner. No Daha and no L function, but here I can make it reasonably complete. So 1 hour must be sufficient, actually, right? So here we are. Breakthrough appeared to be exactly here, right now, with some result. Yes, please. So, sorry? Oh, yeah. All definitions will occur, right?
Like what kind of a state?
Oh, yeah, KZB, let me just mention, KZB, книжник за малочку Бернарда, this kind of superconformal field theory, this kind of conformal field theory, to be more exact, right? There's some connection with, more seriously, there's some connection with K theory of Grossmanian. So indirectly, but still connected with superconformal field theory here, right? Let me skip it, right? First of all, really, it's long story, and this is special situation. But anyway, the point, KZB, QKZ, it is conformal field theory, definitely. There is no question about it, right? So if you wish, remove S here, right? But anyway, this is definitely some kind of part of this particular story here. So why I'm doing this? Because if you here consider S duality, not exactly S duality, a little bit different duality, but we call it less duality, right? As you go all the way, right, you have some kind of important discovery. It will be fundamental functional equation. Will be functional equation, the most fundamental functional equation. Here we are, right? S duality here, in the height is q to t minus 1 symmetry. You go all the way, it is functional equation, right? So here it is functional. Hasse-Weil equation, exactly. So if you go all this way, right, from this guy to this one, to Landau-Ginzburg, and then one more arrow to this particular one, then you will get something very remarkable. S duality, but this is like different than just what we discussed here, right? And then finally you obtain functional equation. Okay, the story is pretty much obvious. We connected one of the most conceptual and one of the most important concepts in superconformal field theory with one of the most important concepts in the whole mathematics. Zeta functional equation is just really something which we all of us are doing. Okay, let me now do to avoid further questions. Let me delete, and then I will begin with definitions. Again, the purpose is actually mostly to introduce conjecture, but let me do it slowly. So first theorem will be the key. Then I will discuss instantons, some new and really nice formulas about instantons, just classical Nakajima style, Yoshikov style theorem. Okay, so we're done. Let me keep it on the blackboard. This is safe. There will be no more questions. I believe just some kind of declaration of intention. And then we begin with plane curve singularities. Right. First topic. Simple. So let me consider F, which will be C, or mostly almost always finite field FQ here. We're doing singularity, so we consider a formal series in terms of x and y, and this always divided by pxy. Pxy can be assumed a polynomial because you can change variables here, right? This means that you impose this relation, right? Pxy equals 0. This is definition of the ring of plane curve singularity. And immediately, if f is C, you have the key notion here, the notion of the link, right? You take a small sphere, intersect it exactly with this equation, which can be considered a polynomial, not a series. Generally, series is not a problem, but let me assume it's a polynomial. Here we have definition of the link associated with plane curve singularity, right? Definition. I will consider only nodes. I will assume that the polynomial P will be absolutely reducible. Over complex numbers, just irreducible. Irreducible, right? So the first surprise in this year is actually I don't need this particular P. Of course, it is necessary if you want to go all the way to Buffer-Warner or to anyway Landau-Ginzburg story here. You need, of course, this particular guy. You need for something else, but not today. So today I will use alternative definition, which is based on uniformization. So let's consider. So you can embed uniformization here or normalization is a very, very simple construction. You just consider f of one parameter, uniformizing parameter z, and let me call this guy, which will be so much important forward, right? You consider embedding, and of course, to match this definition, there must be two generators. generators are always not exactly algebraic, but if you allow series in terms of this particular guys here, two generators, X and Y here, and then standard condition, which is the reducibility. If you consider localization of this particular guy, must be the whole thing. The whole thing here means all formal series when you allow poles here. So two conditions which are literally the same. So equivalent definition. And interesting story that you really don't need P, and they will not need it today at all for all definitions and for calculations. The point is that even for beyond torus nodes, even for relatively simple cases, equations can be quite complicated, and it's counterproductive to calculate for them. They are really not necessary. Okay, so this is definition. Subrings satisfying these two properties, right? This means the reducibility. Two generators. Okay, so little something about theory, third number. So what else can it be? Just you divide O by R and consider dimension. Dimension of this particular guy, right? And conductor. Conductor will be the key. Conductor. So it is pretty much obvious that if you consider principal ideals inside of O, this is classical undergraduate at least algebra here, right? So this will be ZI multiplied by, even simpler because you consider formal series here. That at a certain moment, this particular guy will belong to R, just because it's finite dimensional, right? Very simple stuff here. So conductor by definition means exactly so. Plane theorem, classical here theorem is that for plane pure singularities, Z to delta in this sense here sits inside R. Exactly, if you know delta, you know exactly the first place. The first place when it happens. Okay, it is to delta is mean, the smallest possible. So this is conductor by definition, the smallest possible guy here. If it is not plane of singularity, but it is still to delta, it is called Gorenstein. Gorenstein can have many generators, not only two generators, any number of generators. It can be to delta or smaller. If they coincide, Gorenstein. What I will do today, I will do just, at least in the beginning, I will go over this. Okay, two facts, guys. The delta, third number, which is nothing else but arithmetic genus, actually, right? Literally the same. And classical stuff, then to delta, really very classical, very old. That to delta is the first place after which all this Z, all these powers of Z will sit inside of this, on the side of this particular ring. Okay, so we are well equipped. And now let me introduce the notion of, let me go to ranks first, right? Ranks are actually important, they're relatively new. With instantons, you of course know that we really need ranks all the time here. So let me just make a couple of definitions. So anyway, standard modules, right? Standard modules. Standard terminology, torsion-free modules supported at 0, but I need just something very, very simple. Modules, right? So from now on, N will be rank. In classical instanton literature, actually it is R. Rank means that M will sit in all N. This is important, not inside ring, otherwise it is a Hill direction. It is a quad direction, so inside of this particular guy. So you need normalization, right? Perfect, right? And then the standard. Standard means that if you take M, right? Sorry, R modules. R is on the blackboard here. But if you multiply it by O, you will get the whole thing. This is exactly the condition of being standard. Very simple. Generally, it means that this M must contain, even here you have E1, E2, En, etc. There must be here inside of M E1 plus lower terms, here E2 plus lower terms, and so on and so forth, right? Uniform definition. And then I'm ready, so believe it or not, I'm ready to introduce H Motivic. Oh, sorry, Nakayama rank, and then I will be done. Nakayama rank is simply the number of generators. So dimension, let me do it using Nakayama lemma here, dimension over F. Rank Q, from now on, I will use F. F Q. Complex numbers will be necessary only to connect with the ring. So FQ, right? And this is dimension of module M divided by maximal ideal of R. All rings are local, which is just a guy. If you use XY here, of course, we'll have XY here. So we'll just generate the ideal generated by X and Y. Remember, XY are generators, two generators, X and Y of this particular guy. Examples will follow right away. Okay, let me first put the formulas and then examples. Then we'll consider examples here. So here we go. Maximal ideal and H Motivic. Just let me finish with this particular definition. I will immediately provide a couple of key examples here, of course, including torus knots here. So here we are. You consider T as already promised, then degree. I can put direction, but still let me use degree of M. Dimension O to N divided by M. What else can it be? Right? Divided by M. Degree of M, then to make it just classical, like for zeta functions. Degree of M here, we have T, right? Okay. And interesting story, we have A. U to N, right? This very N. Q to N, the first guy here. Then we consider products, right? This is the best way, actually, really the most canonical way to introduce ranks of modules here. The last guy must be rank Q to differ it from this particular rank Q of M minus 1. Or it can be 1. If it is just a rank is 1 here, then it will be just 1 here. The product will be empty. Empty means 1, as always, right? Okay, so here we are, right? And then let me put here M stand. Summation of M standards here. As we already discussed, dependence on T is here, dependence on A is here, dependence on Q is through the counting of these particular guys here. And of course, there is a lemma, but the proof is immediate here. Lemma, the total number of standard M's here will be fine. This particular set is fine, right? The proof, because it is standard, it contains conductor, our guy conductor, Z to delta times 2n here, right? Standard means it contains E1, E2, En here, then multiply it by O, right? And then you'll get standard, this particular standard modules, right? Standard modules, two conditions. There are invariant seeds here, and then standard means that they contain E1 plus lower terms here, E2 plus lower terms. And then if you multiply it by O, because this conductor here, then definitely they will satisfy the same condition as for A here. So here we are, right? O to N. So what standard module means that it contains E1 vector, right? E2, E3, etc. here, plus lower terms, Z multiplied by something, Z multiplied by something, Z multiplied by something. Yeah, exactly. Yeah. The first guy must be M. If rank is 1, the first guy will be exactly this. If it is empty summation, product is empty, then 1, as always. Product of empty number of terms here is 1. Like in questions? Simple. This is the first guy. When n equals 1, begin with this particular one. If rank is 1, then, right? Then it will be just 1, right? Product of empty number of terms here. Okay. The same definition will be for instantons. For classical instanton, Nekrasov, Nakajima, and many people. Yoshika. Okay, so this lemma, right? Lemma means that these guys, modules, whatever, vector spaces are trapped within these two. So definitely it is finite, moreover, it is like Grassmannian now, right? And then definitely they are only finite, right? So the whole point. This is the difference between Hilt. Hilt means series, always a series, right? In this Quot approach, right? Always the sums, all sums are fine. A serious question here is about uniform depending on Q. On T, it is a polynomial manifest. In terms of A, it is manifest again. But in terms of Q, it really depends on some geometry. Right? So this is the merit of Motivic approach. We need to prove that this polynomially before anything, that it depends polynomially on Q here. Because of this summation, which is not explicit here, right? Not some kind of summation. Their dependence can be different. If it is elliptic curve here, but I forget about this particular stuff here, there will be some Frobenius eigenvalues, etc., etc. But this is not. This is rational. It is called a polynomial gross manifold, right? Okay, so what is compactified Jacobian of rank n? Just this particular guy. This is Jack, right? Bar and n. Let me put that here. The only thing that I here skip some kind of global like projective structure here. So here it is, right? If it is rank is 1, then it is literally compactified Jacobian. So standard module, very easy to remember. Standard modules, right? Always in all theories here, they are by definition compactified Jacobian with one reservation that I didn't show you projective structure, right? There are some standard lemma, which were known, well known, anyway, quite a few years ago, right? Okay, so here it is summation over compactified Jacobian, or to be more exact, compactified Jacobian of rank n here, when we consider bundles. Of course, it is connected to, we will see, you will see example here, it is connected with many things. Okay, now let me do the following. Once we have this definition, and before introducing instantons, it will be literally the same definition here. Let's consider examples. So examples, right? Torus nodes, TRS here, right? The corresponding link will be over C, of course, will be TRS here. Here we are, right? The corresponding R will be F, always FQ from now on here. Then X will be Z to R, Y will be Z to S. Of course, equation will be X to S equals Y to S, but I don't need. So here we have R, right? Delta R minus 1 multiplied by S minus 1 divided by 2. This fact is due to Sylvester. Many years ago, this Frobenius coin exchange, nothing else. You just have this particular guys here. So accordingly to delta and stuff like this, and so on and so forth here. Okay, so quickly, I don't have much time for this, but still, let me assume that n is 1, and this guy is trefoil. Let's calculate superpolynomial. Perfect, right? That's superpolynomial. Let me show you that I was serious when I mentioned it is about 3 minutes. Okay, maybe not 3, but a sort of 3, right? FQ, what is trefoil? So Z cube, pretty much always I will assume that R is greater than 3, and this square, right? So 2 guys here. Perfect. Delta is 1, right? Modules, standard modules, rank 1. It can be O, right? Rank 2, Q rank is 2 here. And then it's very easy to see, look, what is conductor here? Z is missing, right? Z squared, Z cube are present, then all of them will be present. And starting with Z2, right? All of them will be present, but we know this because 2 is 2 times delta, delta is 1. Perfect, right? So there is only one possibility. There will be another family of modules here because they are standard, they must begin with 1, right? So there will be lambda and Z, right? And then we can skip anything because modulo, all of them contain, you remember, Z to delta here, so we can just reduce them to n equals 1 here, right? So 2 families, right? 1 family, and just 1 single module of rank 2. Here, of course, rank is 1 generator. 1 generator, right? Here, rank is 2, definitely, right? 1 and Z. Perfect. So 1 plus QA, right? Plus QT, because they are of codimension 1. T, right? Codimension, remember degree is 1, right? How many lambda? Lambda can be 0, of course. U, right? So here we are, our first formula. 3 minutes indeed. So QT plus QA. This is a super polynomial. Nisha, I believe, began exactly with this particular one many years ago, just super polynomial in some notations, maybe, which are not exactly what he used long ago here. Super polynomial for trefoil with QT parameter here, right? And the claim is that this is a unique approach when the proof of this formula is comparable with this length here. No need to do anything. So just immediate calculation, right? So super polynomial, Motivic, and let me put here 3 foils. Here we are, right? Yes, lambda can be 0. If lambda is 0, it is R. Good question. If lambda is 0, then M is R. Yes, yes, it is standard module with one generator, right? Definitely R is standard. The simplest examples are exactly the whole thing and R to N, right? So this is exactly the one. So it can be 0. For Hopf length, because of some reason lambda is non-zero, it will be a little bit different formula. Hopf length Q minus 1T. I don't give any definition, but this will be the formula for Hopf length. Pretty much the same proof, actually, right? But I didn't provide any definitions. Okay, perfect, right? So 3 minutes, as I promised, right? So example number 1. And example number 2, non-torus case here. So let me just consider one particular case here. So just to save time here, right? So classical example will be this 6 plus this 7. This is really the simplest non-torus case, algebraic, but non-torus in here. And here, Z to 4 here, right? So the favorite example of Zariski, by the way. So they're very simple to calculate. 8. I will skip the technology how to calculate here. And then, so what is the corresponding, one interesting story, what is the corresponding cable? Cable is 13, 2, T, 3, 2 here, right? So again, this is definitely non-torus, not quasi-homogeneous, right? And the cable is like this. This is famous cable because it is the smallest possible cable, which is algebraic. T32 is non-algebraic. This cable is non-algebraic. This is the smallest non-algebraic. Okay, so perfect, right? Generally, of course, it can be 7. Then plus it must be relatively prime with 2 here. Then 9, 11, and so on and so forth, right? So, series of obligations. Let me stop here and go to instantons. And we're pretty much ready. So instantons. Instanton sums here, first of all, 3, and then so definition. Sorry, I need some notation. So now there is no O, but we have classical stuff, which is just the guy which is actually C2, but it's not C2, it's local C2 here. So here we are, right? So just 3 parameters, X and Y. In instanton theory, we're supposed to say, let's consider modules supported at 0. Well, a lot of connections. If you know this guy, you know everything. Of course, you know all the formulas for A2. This is the key guy here, definitely the story. So what is M? A invariant sitting inside of A to N, N standard. Oh, no, just this, just any module exactly of this particular kind. See, M invariant module here sitting inside this particular one here. Just free theory, right? Later there will be some conditions. So what is instanton time? Just see. Instanton, Nekrasov, honest Nekrasov instanton in the rank time. But with this reservation, if I remove this brackets, it will be exactly his formula. His formula, the formulas of his predecessors. No stuff here, just M here. T dec M, right? And just copy this. Here to N, right? 1 plus A, U rank U of M minus 1. Right, perfect, right? Instanton sums here. Dec, but you can already understand what I'm going to say. Dec will be dim AN divided by N. It is supposed to be finally dimensional, because otherwise it makes no sense. Okay, perfect. So here we have definition. Of course, it is infinite, right? And then the end of the story. So it is instanton sums here, right? Then instanton sums with conductors. This is a little bit new, but not too much new, just because of rank and because of this letter A. But A appeared in the literature, so it is not really new. But this is new. let me assume that this guy, I will call it conductor, is any ideal, find co-dimension as always in this business, any ideal in H. Any ideal, which we will call conductor. Conductor here, right? Same. Right? Slice rules exactly all modules which contains this particular guy. Sorry, A to N, of course, submodule. Okay. Actually ideal, but it will be ideal, but still exactly this particular one. This is slice, instanton slice. Theorem. Theorem 1. Connection between instantons and superpolynomials. Okay, so just copy that. Right, theorem 1, right? So, and here also, here I need to put this particular guy, and this particular guy will be, let's do the following. Let's call this guy C. C will be Z to the delta here. Then let's consider C to N and tilde. Tilde means the, that we call it exactly S here, right? This particular guy. So you take C, consider its lift, complete lift to R. You remember R is covered by A here, right? So as here you will have C tilde, the complete lift of C. C will be this particular guy here. And then consider S power theorem, right? So which connects Motivic without any loss of information. If you know this guy, of course you know Motivic polynomial. Right? Perfect. This is from my paper, Journal of Algebra 22, Journal of Algebra. Just a second, 2022, right? Please go ahead. Slice is just, instanton slice is just, let me put it like this, as I know, like this slice, which depends exactly on this particular guy here, right? So take any ideal, right? Any ideals, right? But here in this particular theorem, we have quite a family of slices which are exactly conductors to N, right? So begin with a plane curve singularity, right? Consider the corresponding conductor, right? Consider this particular guy, well done, right? Interesting message. It appears that superpolynomials, Motivic depends actually on conductor and nothing else, you know, right? Which I used again a lot in Journal of Algebra 2022. So perfect, right? Since still I cannot relate, let me show a beautiful formula, theorem 2. So beautiful formula is like this. Let's consider free. I follow Nakajima, but it is not new, definitely not a new formula here. I will explain why it is so much important for what I'm doing. Sure, because there were two papers, very important papers, right? Not in their papers, but still I use pretty much the same technique to prove it. Let me do the following. Let me consider three theory, right? But let me assume, let me fix the number of rows. I need to explain what I mean by this, right? Little something. Let me just use this particular space. I don't need examples, so I will go to this. I will show again the here. So little something about classical instanton, the beginning of instanton theory. which is about monomial ideals, right? So standard stuff here. I prefer to have it on the blackboard. So monomial ideals, right? Depends on Young diagrams in the following way. You consider Young diagram, for instance, like this here. Then you put here 3x cubed. Let me make it like this. So here it will be x squared y. You will immediately understand what I'm doing. Y squared here, and here will be y to 4. Here we are, right? Monomial corresponding monomial ideal will be the span of all this. All monomial ideals, which ideals generated by monomials are of this particular kind, one-to-one with Young diagrams. So we will call I lambda, just about this particular guy. If you have lambda 1, lambda 2 sequence of these particular guys here, it is pretty much the same. Monomial ideals inside A to N, right? They're just one-to-one monomial ideals for this particular guys. So what is the passage? The passage is fundamental. Give me any, for instance, let me consider one-dimensional case. Then consider leading terms here. Consider the operation leading terms. Look, I don't use this direction. It is not necessary at all. Leading terms here, more which is simply not. Leading terms means that I need to order them. X will be much greater than 1, and y will be much greater than this, right? So then the claim, leading terms, of course, they are monomials. They will form monomial ideal. And they keep, then automatically this guy is I lambda for some lambda. And the point is, lemma, which is simple to prove, but absolutely fundamental, that the cardinality of this particular guy, the number of boxes here, is literally degree of I. Same for sequences, but I will skip it. Just same when you have lambda 1, lambda 2, lambda n, when the rank is empty, right? Just a little something, let me keep it on the blackboard, right? This particular stuff. But now you need, of course, to go to arbitrary instantons. And let me show you a beautiful formula. Just delete everything. Just to save space here, right? I already mentioned the Kajima. Yoko should say it. So H, right? Now let me assume that diagrams, right, are with L, no greater than L, right? And the claim is, surprise, surprise, that why it is surprising, I will explain in a second here. So J equals 1, right? N, and here you will get 1 plus A, right? In spite of this high sound complicated expression, it is extremely simple in the free case. N times I plus 1 here minus J Ti, right? So then divided by 1 minus Q to Ni minus J T2I here. Here we are, right? The formula, when you fix the number of rows, which is not unusual in this particular business here, and then you obtain this particular fantastic, very nice formula. Exactly here, right? Because of denomination, it will be invariant series, of course. Okay, so why it is somewhat non-trivial? So there are some traces of this formula, actually more or less equivalent statements here when rank 1, right? But when rank is n, as Nikita Nekrasov used to say, actually, he really likes it. He said that it cannot be too simple because modes talk to each other, because components talk to each other, right? So it is complicated. Still, in spite of all this, the formula is exactly like this. So 2 proofs. The first I already mentioned, using the Kajima Yoshoko here, your Yoshoko here, right? And the second, thanks to this theorem, this is lim of Motivic polynomials, right? Motivic polynomials, superpolynomials here. So we are considering the limit, assuming that they are conductor, they are anyway approach exactly like this. Their conductor, right, contains whatever this particular guy. starting with some n, all conductors will be inside of this particular. Assume that conductor tend to 0 within this particular condition. So an alternative proof. If I know Motivic polynomials, I can prove this formula independently. I can show you some very remarkable implications. I can really capture this particular guys here directly even now. But let me stop here. So this second alternative proof, just using curves here, just using Motivic polynomials. So this is theorem 2, so theorem 1, right? Which I promised. Beautiful formula and theory of stabilization independent of independent interest, stabilization of Motivic superpolynomials. You see some non-trivial substitution is necessary here, right? So theorem 3, and I have 5 minutes, but we are doing fine. Let me state conjecture, and then there will be the rest of the story will be theorem. Well, let me just understand. Huh? Yeah, please go ahead. N rank, instanton rank. R, in classical instanton literature, M and R, it is R actually, right? Instanton rank. Rank actually, rank through all these theories. Rank, right? Instanton here, everywhere, here, so N. Right? And of course, the same inside of R here. N, letter N, right? If your question about letter N here, right? N, everywhere there's N. Hmm? Sorry? Some number, some 1, 2, 3, 1 can be 1, then rank 1. Scalar instanton here, right? H, right? So this is this super polynomial. So Havanov, etc., then Motivic super polynomial. If you know Motivic polynomial, you know this particular new guy here, right? Okay, let me show you what I promised, the discovery, right? No, just connection. One theory, which is all 4 which I mentioned, appear to be connected pretty much directly with instantons, right? The limit of super polynomial, it appears the connection is like this. If you want to capture whatever, Nekrasov, Nakajima, many formulas, consider super polynomials, whatever, use any theory you wish, Havanov, Rozansky, for instance. Consider this particular substitution and the limit, you will get these formulas, right? The end of the story. We connected at last, connected two super directions here. Instanton direction, right, which is about surfaces here, and the direction about algebraic nodes or about any nodes here. And then discovery. And then as much as I have time, or maybe later, so maybe it's about time for me, I have like discovery, right? That first of all, let me show you example. For the first case I mentioned, let me just show you example which I already mentioned. Just give me 3 minutes, right, and I will be done. So this is exactly for this particular lambda. This guy is conductor C, rank 1 only. To simplify our life here, n equals 1, right? So it will be C exactly for example, which I called cable 13.2, torus 3.2. Let me skip completely theorem 3 here, right? So this is the answer, right? So this is exactly how to calculate conductors. Journal of algebra, and then let me mention some of the stuff here. Mazin, Gorsky, etc., but they don't calculate conductors. They created the combinatorics of sparking functions here. So this is the first non-trivial example. For torus example, it is even simpler. Okay, just to show you one example, right? So what happened if this is combinatorial, this is what they consider. There's some Dyke path here, right? So Dyke path exactly for this particular case. Right? Okay, just to show you one example of non-trivial conductor. For torus nodes, it is simpler. Then the point what I'm going to do, in contrast to what they did, I'm going to remove this particular box here. Perfect, new theory. So now let me consider I lambda prime, take another guy S here, exactly for this particular diagram here, which will be I lambda prime, right? So I'm leaving algebraic nodes here. What is the answer? What is the corresponding So I take this particular guy here. The claim is that the corresponding polynomial here, exactly this particular one, right, will be K 13, 11, 2, non-algebraic, 11, 2, torus 3, 2. Right? So the first example, when I managed to obtain from Motivic theory, which is about plane curve singularity, something which is not, right? But this is not the most impressive. What is the most impressive and simpler, actually, is when you take, so now I'm doing the following. I'm taking all possible ideals, but first I begin with monomial ideals, right? Then let me just take this particular guy, right, which I already promised. So here we are, two blocks here, right? Let me take this particular lambda, right? This is not a conductor of any algebraic cube. What is the corresponding H inst, right, depending on this particular one? This is just I lambda here, right? Here we are, K12 and 242 immediately, right? So I just I relax the notion of ideal here. Next example of the same kind, not that famous, but still famous enough guy. Let me take this particular diagram. K12 and 725 here, but not that famous, and so on and so forth. There are many examples here. So the point is that I can now I can relax this particular condition. I leave completely and absolutely leave plane curve singularities. They are not, absolutely not. Moreover, X and Y are on equal grounds. Now it is up to me. Moreover, I can consider ideals which are not monomial. So there is a lot of experiments here, but I'm -1 minute here. Let me state conjecture, skipping anything else. So conjecture is that if the corresponding H inst, right, we left completely plane curve singularities. There are no algebraic curves here. If this particular guy with n, or let me make it n equals 1 here, n equals 1 here. If this is super dual like for Daha, just give me please 2 minutes and then I will be done here. So for Daha it is q to t minus 1, Daha parameters, but here we have substitution. So it will be simply qi tj will go to qi t delta minus j plus I, right? So this is substitution. If it is invariant for this particular institution, super dual, then the claim that it coincides with Khovanov-Rozansky for some hyperbolic, almost always hyperbolic, for some knot here, which is given by combinatorial construction due to Galashin and let me at least put the name, at least one, Galashin and Lem here, right? Some kind of standard, give me Young diagram here, and then I can calculate it. It's very simple, the corresponding braid. And then close this braid here, here we are, right? So anyway, because of some reasons, you need to assume that it's super dual here. Okay, this is pretty much the end of the story within the time I have here. The end of the story. So we completely left plane curve singularities. Now we have ultra simple definition, which is exactly instanton slices here, right? And then they appear that playing with these particular guys here, conductors, right? I call them conductors. You can obtain a lot of hyperbolic and not only hyperbolic rings. Again, I need to show you some examples, how many of them, and so on and so forth. Now it seems that I'm done. If you have questions, it will be my pleasure. Am I right? I'm done. Minus 2 minutes.